So let's move on to the part B here, and I can take this to the next page. Okay. So it says here, assuming the data above were collected differently. Okay, so pay attention to this. And how differently was it collected? It says the first 4 randomly selected volunteers completed an obstacle course with a patch over the right eye, and a different group of 4 randomly selected volunteers completed the same obstacle. So let me say the same here. The same obstacle course with a patch over the left eye, right? So you have 8 people, right? The first 4 volunteers did that with the patch over their right eye, and the second 4 volunteers, who are totally different, did that with a patch over their left eye, right? In part A, it is the same person that did this twice, right? The same individual did it with their right eye covered, and then they did it again with their left eye covered. But in this question, in part B, we now have 2 different sets of people performing with their right and their left eye. So let's read further. It says, the complete, let's remove and here and make this a better statement. Okay, so the completion time is the same as recorded in part A above. So it means that, this is just to save you time calculating or doing a lot of work. So it means that our data is still the same as what we have here. Okay, and let's put it underneath here. Okay, the only difference this time is that these are from different persons, right? These are 4 different persons, 4 sets, right? And then you have different 4 set of people, okay, performing this. But in A, they were the same person who did it twice with left and right eye. So from all that understanding, what this simply means is that this question is trying to make you solve this problem as independent t-test, right? So let's start in our responses and explain further. So what this technically mean, let me go back to red again. What this technically mean is that the appropriate test this time in this scenario as described in part B will be independent sample t-test. Okay, to be complete, we'll say for 2 population mean. For 2 population mean. Okay, and this could be said in several ways, right? So read through the text or read through as you're completing your homework. This will be 9.2. As you're completing this homework, you would have come across this as well, right? So it could be said this way or so many other ways. I could say 2 independent sample t-tests. Okay, but the key thing here, let me turn to green, is that you are doing an independent sample t-test, right? And the word independent, we automatically imply that you have 2 groups, right? Because you can't be saying one group can be independent of itself. So you need 2 groups to use the word independent. They are independent of each other. So that is the appropriate test here. And again, you could use this, You could use any other format you see on the text, but it should contain the key thing. And the key thing is that you're conducting independent sample t-test, or you can emphasize the word 2, independent sample t-test. And for completion, you can add for 2 population mean, right? Okay, so say this in whichever way, but emphasize the key thing and you get credit for that, or the correct credit for that. Okay, so the next question is to state the null and alternative hypothesis. And so here, come back to red. The null hypothesis will be that mean of the first group, let's call them the right eye group, is equal to mean of the left eye group. Okay, so unlike part A, this will be our final null hypothesis. I don't want to change this to any other way, right? Because these two groups are different from each other. But we're able to kind of try to use mu D because in part A, it is the same person that did it twice. So here, since they are different, our null hypothesis should remain this way, okay? And then the alternative, of course, let's move this back. The alternative hypothesis should be that they are different. And let me look at the question to be sure that is what is implied. Mu2, mu L rather. Okay, so let's look at that question. Let's see. Assuming the data above were collected differently, okay, in the first four randomly selected volunteers, complete the obstacle course with a patch on the right eye, and a different group randomly selected volunteers completed the same obstacle course with a patch over their left eye, okay? The time is recorded above. What's with everything else being equal as in part A? So I'm saying the statement here, everything in part A should be taken the same way. So when it says, this is the question you're investigating the difference between the two, because it says that, then that's what we're doing, right? But maybe I could make that clearer by copying this question and putting it here, just to be explicit, okay? So everything being equal, right? Then I could put this as a question here. Is the average time to complete the obstacle course different when a patch is placed over the right eye? So let's have that question here, just to be very, very clear with what the question is asking you to do. And also just to be abundantly clear, let us also copy the assumption here that was stated in part B. Okay. Yeah, but when this says with everything being equal as part A, I expected all this to have been understood, right? So let's put it here for completeness. So I say, assume a normal distribution, what can be concluded at alpha of 0.01, significant level, okay. Did I ask you a question about the significant test somewhere here? Oh, I did not. Okay, no problem. I think it's in part C. Okay, so with alpha level of this, is the average time to complete the obstacle course different? So again, we are saying, are they different, right? So I'm going to come over here, and we know that our alternative hypothesis is as we stated it here, whether they are different from each other. Okay, so let's go ahead and compute the test statistics. The test statistics for independent sample t-test, right? It's a t-test. Let's put independent here to make it clear. The test statistics for that, if you follow through in our work, is mean of group 1, sample mean of group 1 minus sample mean of group 2, right? Minus the population mean if you write it fully. Okay, all divided by the square root of variance. Let me write that well. The square root of the variance of group 1. So the variance of group 1 will be the square root of the square of the standard deviation, right? So I could say standard deviation of group 1 squared. I could just say the variance, right? Divided by group 1 sample size plus the standard deviation of group 2 squared, which will be something as the variance, divided by, what is that? Control Z, that's not working. Okay, give me a moment, let me take care of this. I don't know where that is coming from. Okay. Let's cover this again. Divided by sample size for that group, okay? So this is our t-test statistics. Okay, but as explained in the video in chapter 9, we can simplify this further. Can make this look a little bit less complex, because we know that all of this is equal to 0, right? Because again, if you take it from here, let me use green to explain that. If the null is true, then all of this will be equal to 0. So if the null is true and the null says that mu of group 1, right? And okay, so I'm going to correct that later on. Mean of the right, those who did it with the right hand, is equal to mean of those who completed the obstacle course with the left hand. If this is true, then it will imply that you can rewrite this as the right group minus the left group is equal to 0, right? Because if they are equal, then when you subtract them from each other, you should have 0. Right, so automatically this part of the formula will tend to 0. Let me go to red so we can write it in a less more harmonious way. So t-test for independent sample would then be let me do this, would then be just mean of, and let me use a right hand minus mean of left, just to make it clear, but you're having 1 or 2, group 1 or group 2. Okay, so mean of left, so this is supposed to be your group 1 and this is your group 2, right? Divided by, if I have enough space there, okay, I do, divided by the square root of sample standard deviation for the right hand, which is your group 1, all squared. This is happening again. Okay, all squared. So we're taking the square root of this all over n of the right hand side, which is your group 1. I don't know why this is happening. I think there's something going on there. So let me finish up that. This is n here. And I think this is what I have. Plus the standard deviation for the group on the left hand, which we are using as our group 2, squared divided by n of, these are interesting. If I'm trying to put this arrow, it's not going to magically come as beautifully as the way they are coming in here. Okay, divided by n of left hand, and this is our group 2, right? And this is square root. Right, so this is a more harmonious form of the formula, but I'm going to remove all these R and L, not to confuse you, but I'm putting that here to make it clear where you're getting your values from, okay? Maybe finally, stated more simply, the t-test for independent, for 2 independent samples would then be just x bar 1 minus, I wish I could use undo to remove all this when it comes. Will be x bar 1 minus, okay, this is becoming too much. X bar 1 minus x bar 2, all over square root of the standard deviation or squared or variance of group 1 all over sample size of group 1 plus variance of group 2 all over sample size of group 2, right? The square root of all of that is your denominator, okay? So let's go ahead and move on here. Okay. So these are t-tests. So what you need to do next is to kind of list out what you have and what you don't have, and then go ahead and get what you need, right? Okay, so We could start by noting that N1 is equal to 4 and that N2 is also equal to 4, right? So we got that taken care of. X bar 1, we need to get that. X bar 2, we also need to get that. Standard deviation of group 1, we need to get that. Standard deviation of group 2, or the variance rather, of group 1 and the variance of group 2, we need to get that. I think I will keep it to standard deviation here so that when we are putting it into the formula, we can then do the variance. Let's see if I can actually use the eraser. Is it possible? Uh-oh. Okay, that is not working. Maybe I should pick it up. Yeah, a lot of little tiny things wasting time for this. I wouldn't edit this, but I know that you can, maybe skip forward here. Okay, I'm just gonna kind of take this off and write it again. I think it's quicker. My tools are really malfunctioning here. So N1 will be 4, N2 will be 4. X bar 1, we need to get that. X bar 2, we need to get that. Standard deviation of group 1, we need to get that. Standard deviation of group 2, we need to get that as well. So that way, when we are done, I can put it in here and raise it to part of 2. So let's move it down to it. Okay. So looking at this, how do we proceed? We simply find the mean of group 1. So let me put that data down here so it will be easy for us to pick up. Let's make a copy of this again down here. Okay, so the mean of group 1, and I can do this table to make it clear, make it easy. Sequential. Okay, so the mean of group 1, so let's have our data for group 1 here. Let's call it X1. So I have 49, 47, 44, and 46. Okay, so their mean, the mean of group 1 is the sum of all the data in group 1 divided by how many data I have in group 1. Okay, so if I add this and I need to, maybe I should use the computer calculator to, so you follow me. Yeah, so if we add these numbers here, we have 49 plus 47 plus 44 plus 46 is equals to 186, right? Just do this again, just for clarity. 186, so I have clear out this. 49 plus 47 plus 44 plus 46 is 186. So that is my sum there. Can minimize this. So the numerator I have 186. Okay, and of course I'm dividing this by 4. And when we do that, you see that for X1, their mean is 186 divided by 4. So let's get our calculator back. 186 divided by 4 is going to give us 46.5. So you have 46.5. So that is your mean of group 1. Okay, we can go ahead and calculate our mean of group 2. And remember, group 1 is just those who did with the right eye covered. Right? For mean of group 2, we could say left eye here. This happened again. Interesting. Okay, so we could say left eye here, covered. For their mean, group 2 mean, we are going to be summing up the data under group 2. We're going to be dividing that by how many sample size we have in group 2. Okay, so again, we plot our calculator and clear everything. Here we have 46 plus 44 plus 42 plus another 42, and that gives us 174. I will just do this again to be sure. 46 plus 44 plus 42 plus 42 gives us 174. So the numerator here is 174, and we're dividing this by 4. Okay, the magical arrow has appeared again. 174, and we're dividing this by 4. Okay, so let's pull our calculator and complete that. 174 divided by 4 is equal to 43.5. So our mean here is mean of group 2 is equal to 43.5. Okay, so now that I've gotten the mean for both sides, remember I am doing the mean separately this time because we are considering this as independent sample. So this is 46.5 and this is 43.5. Okay, another interesting shape came out here. Okay, so I'll go ahead to get their standard deviation, right? I already started working group 1 here, so let's complete it. So here I'm going to have xi for group 1 minus their mean, right, squared. Okay, so we're going to take 49 and their mean is 46 minus 3, right? I will be doing this on my calculator. So I'm going to take 49 and subtract 46.5, which is the mean, and then square that. And then, so if I implement this thing here, the numerator, what I have for the first line is 6.25. Okay, we're going to do the same thing for the second line. So again, take 47, subtract the mean for that group, which is 46.5, then raise it to power of 2. Okay, so let's do that. So 47 minus the mean, which is 46.5. Okay, and raise that to power of 2. I got 0.5, raised to power of 2 will give us 0.25. So over here, I have 0.25. Okay, so it's like my writing tool is producing all kinds of shape today. 0.25, that's what you have there. So go to the next line, do the same things. I'm going to just do it quickly. 44 minus 46.5 is going to give me negative 2.5. Raise that to power of 2 gives us, again, 6.25. Okay, I'm trying to understand why that's the same as the other. Okay, 6.25. Then I do 46 minus 46.5. Okay, that gives you negative 0.5, raised to the power of 2 gives us positive 0.25. 0.25. Okay, so when I sum this up, I'm going to get the standard deviation. Sum it up and divide by n minus 1. So remember, for group 1, let's say standard deviation for group 1, we are looking at the square root of the sum of, okay, this is really wasting our time, but there's nothing I can do. We're just going to keep on taking care of it whenever it pops up. So remove that and this as well. We don't want to. Let's go ahead and continue. So the square roots. Okay. I think it's time for me to get another divide. This is really a mess. Okay. So let me just write the formula first and then we'll put in the square root of each data point minus the mean for that group, right? We're talking about group 1 square divided by n minus 1, and we take the square root. That gives you the standard deviation, okay, for that group. So already we have the numerator here, so we just sum these items here, right? We just sum that. So let's do that. 6.25 plus 0.25 plus 6.25 again, plus 0.25 again. That gives us 13. And let me repeat that just to be clear, to be sure that's okay. So we have 6.25 plus 0.25 plus another 0.25 plus 6.25. So that gives us 13. So we have 13 as the numerator. Okay. So over here, this is like saying we should do 13 divided by n is 4 for this group. 4 minus 1 is 3. So we are looking for the square root of this, right? It's our standard deviation. Move this down a little bit. Okay, so if this is what we have, then simplify this. You have 13 divided by 3. That gives us 4.33333. So let me write it over here. So this is like square root of 4.3333 to 4 decimal places. And if we simplify this further, this will be square root of 4.33. I have a different number here. So 4.3333. That gives me 2 points. I think I better write it over. That gives us 2.08117. If rounded up. Okay, so I have this. So that is what the standard deviation for group 1 is. So let's write down that number over there, right in here. So this will be 2.0817. Okay, I hope you can see that. I know what came up over. Yeah, let's see if I can remove this. It's not going away. Okay, so you have that value there, 2.0817. Okay. All right, so we just finished for group 1. So let's go ahead and get the same value for group 2. The standard deviation for group 2. Already we know that the mean is over here, right? The mean is 43.5. So let's create another table for group 2. Okay, let's cross this over. So for group 2, SI for group 2, we have the following data set. Let's see, 46, 44, 42, 42. Okay, so we have 46, 44, 42, and 42. Okay. So we're going to find the standard deviation for that. All right, so we go ahead. So of course, as before, we want to do the data minus the mean, all squared. Okay. Be patient with this. Actually, another one messed up there. So we have 42 there. And then we have our line and our line here. So we're doing the data minus the mean squared. That's all what in this group. Remember the mean for this group is 43.5. Is that correct? It's 43.5. So we just have it written down here to be clear. Okay, so I'm going to go ahead and do each of these minus the mean and square them. So 46 minus the mean, which is 43.5, will give me 2.5. Raise that to power of 2, I'm going to get 6.5. So I have 6.25. So I have 6.25. Look at the next one, 44 minus the mean, 46.5. 44 minus the mean, which is 43.5, will give me 0.5. Raise that to power of 2, get 0.25. So you have 0.25. Okay. Be patient with these shapes popping up everywhere. Okay, okay, can't even write this time, 0.25. Okay, we go to the next, that is 42. minus 43.5. That gives us negative 1.5. Raise that to power of 2. That gives us 2.25. So here we have 2.25. And we're going to have 2.25 here as well, because they are just the same number. Okay, so add this up to get the numerator. And again, remember the standard deviation for group 2 now will be equal to the sum of the difference between the data and their mean squared divided by sample size minus 1, the square root of all of that. Okay, so if I do this, the numerator will be the same as, again, I can use a calculator here so you can participate in that. So 6.25 plus 0.25 plus 2.25 plus 2.25. That gives us 11. Okay. So let's do that again just to be sure. 6.25 plus 0.25 plus 2.25 plus another 2.25. That gives us 11. So the numerator there is 11. So we have 11 here divided by n minus 3. We have 4 minus 1 is 3. So we have 3 here. So it means your S2 standard deviation of group 2 is something like the square root of 11 divided by 3, which will give us the square root of 3.6667. Okay, so if you take the square root of that, square root of square root of 3.6667, that gives us 1.9149 rounded up to 4 digits. So this is our S2. Okay, let's put it over there. That will be 1.9149. So over here we have 1.9149. Okay. So we've got everything we need to compute our t-test statistics. I'm going to pick this up and take it to the next page so we can work with it. So we've got everything we need. So if we pick this up and go to the next page, let's move this down. We're trying just to do the test statistics, right? So the t-test statistics for independent sample, which is given as the mean of group 1 minus the mean of group 2 divided by the square root of okay, this coming up over again. We'll delete it patiently. Okay, that will be the square root of group 1, the square of the square root of group 1 standard deviation divided by sample size for group 1, okay, plus the square of the standard deviation for group 2 divided by sample size for group 2. So these are our t-test formula, okay, written in simple form. But remember, group 1 here for us is those who right eye were covered, and group 2 for us is those with left eye covered. So if we have all that picked up, I think I can paste it here. All the data containing in this. Okay, so we have it over here. We can actually just keep it by the side here, so it will be easy to plug in. Okay. Okay, so if we have all that in place, we go ahead and plug in into this formula. So over here, we know that x bar 1 is 46.3, 46.5, and we know that x bar 2 is 43.5. So this will be our numerator divided by, so we're going to pick up S1, which is 2.0817 all raised to the power of 2 divided by sample size, which is 4, plus, okay, this happened again, remove that and put in 4 here, plus 1.9149 9149 all squared divided by sample size again, which is 4. Right, so this is what we're trying to do here. And let's do them in part. Let's change this arrow here. Remove that. Make sure that this is clear. Okay, so let's go ahead and try to simplify this. We'll do the numerator first. I think it's easy. It should be 3. Just to use the calculator to be clear with that. 46.5 minus 43.5 gives us 3. So the numerator is 3. We're going to figure out the denominator and let's do them in parts. Okay. So first I'm going to do 2.0817 raised to the power of 2. That gives us 4.33347 and all that. So okay. I don't know if it helps to do this. Okay, let's do it in part just in case you are having different thing in your calculator to be sure you know where the error is coming from. So 3334 divided by 4, this is what we have right now, plus on this side I have 1.9194 raised to the power of 2. That gives me 3.6841 all over 4. Right? So if we simplify this further, we should have this to be equal to 3 on the numerator divided by the square root of, interesting. Okay, divided by the square root. Okay, let's put in the numbers first and then the square root later. I think that's what causes the problem. The square root of the first part, which is 4.3334 divided by 4, that gives us 1.0834 plus 3.6841 divided by 4. That gives us 0.9210. Okay, so now I'm going to take the square root of the sum of that. All right. Okay, I hope you're following so far. And this is a video, so you can afford to pause it or go back and all that. Okay, so this is 3 all over. Add those two, just taking every step. You don't have to, but just to be clear, you're following me step by step. 1.0834 plus 0.9210. This will be 2. Is that correct? Yeah, 2.0044. Let me do that again. 1.0834 plus 0.9210 will give us 2.0044. So I'm taking the square root of 2.0044. So this will be equal to 3 all over the square root of that. I'm solving everything in bits. Maybe to model what you may do to avoid unnecessary error. So this will be 1.4157. This has happened again. Let's remove that. 4.4157. Okay. So if you do that for 1.4157, you divide 3 by 1.4157, 3 divided by 1.4157, you are going to get this value here, 2.1190. Or 91 to 4 digits. Okay, so you have this value here. So this is your test statistics. Okay, took us a long way, yeah, but that is what we have. Hoping that everything we worked on is correct. We're gonna do this in class today, and I will post this video, but I will give you this to work and give you time to do it. during class today. So we have the t-test for independent sample mean. That gives us 2.1191. Okay. All right. So I'm going to do the p-value next. So I'm looking at 2.1195. You know, 2 decimal places is 95% confidence interval. Two standard deviation away is 95%. So I will expect this to be, close to 0.05, right? And probably we are going to kind of have a different conclusion in this. But let's see. The p-value, we'll go to our Excel. So remember the test statistics is 2.1191. So we'll go to our Excel. I'm going to do it down here. Okay, maybe delete all these to make that clear. So let's do it down here, equal to t.dist. Again, here I'm doing two-tail. So I'm going to double click on two-tail. And if you want to learn how to do one tail, just double click on the next item. But you can watch the videos under chapter 9. I think we solved one tail then, or maybe chapter 8 as well. So our test statistics is 2.1191. Let me confirm that very quickly. 2.1191, comma degree of freedom. Okay, so let's explain this. The degree of freedom for independent sample t-test. So now they are independent. So you have two different groups. So the degree of freedom is actually the degree of freedom for group 1, which is like n1 minus 1, right? Plus the degree of freedom for group 2, which is like n2 minus 1, right? If you simplify this algebraically, this will be something as n1 minus 1, removing parentheses, right? If you summarize this, you get n1 collecting like terms, right? So this is the formula for the degree of freedom for independent sample t-test. So degree of freedom that we need here will be n1 plus n2 minus 2. Okay, so in this case, we know that each of these is 4. Okay, we know that each of this is 4 minus 2, so that gives us 8 minus 2, which is equal to 6. So our DF here is 6. So let's go back to the Excel and put in 6. Okay, so again, t.dist, and let me start a little bit again for clarity. So this will be equal to t.dist, and I'm looking at two-tail, which is over here. My test statistics is 2.1191, and our degree of freedom we just computed to be 6. Press enter here. We got 0.0783, somewhere close to 0.05. Okay, so 0.078381. 0.07, I think I can actually copy that and paste it over there, not to make a mistake. So the p-value here is actually this, right? Let's write it down. So our p-value turned out to be 0.0, okay, over that. 0.0784 to 4 decimal places, right? And of course, you can keep your final answer in 2 decimal places, which is 0.08, if you like. Okay, so that's all we have here. P-value. Then we go ahead and answer the next question. It says based on the p-value, should we reject or fail to reject the null hypothesis? Okay, so here we know that p-value, our p-value is greater than is it greater? It's less actually. It's less than alpha. Remember? Okay, so let me write this in full. p-value, which is equal to 0.08, is actually greater than, oh, sorry, is less than alpha. Is actually less than alpha, which is equal to 0.01. Is it less? Is greater, sorry. Okay. This is greater than alpha, which is 0.01, right? So if this is the case, of course, we reject. I will fail to reject the null hypothesis. Okay, careful with my statement. I'm beginning to say things that are not correct. So we fail to reject the null hypothesis. So here we, because this is bigger, we'll fail to reject the null hypothesis. Okay, and then the next, what is your conclusion? Your conclusion happened to align with exactly what we have here in part one. They happen to align. We still fail to reject here. Where is that? Okay, so in part A, we also, oh, we rejected here. Oh, okay, so the conclusion is different. And I'm going to just copy this and just change certain things to save us time. Okay, so let's read through this again, okay? So on average, the time to complete the obstacle course when the right eye is covered with a patch is the same. Okay, another way of saying that is that it is not different as the time it will take to complete the same obstacle course when the left eye is covered. Okay. Okay, so I hope you get what we are doing here, even though this kind of become slower than it would have been writing a new one entirely. But I hope that by copying and pasting here, you could see how to tweak your conclusion to match what you are saying. Because here we have that the null hypothesis is that the mean of the right eye is equal to the mean of the left eye. And we failed to reject this, right? We failed to reject. And because we failed to reject, if we have rejected it, we would have supported the alternative, which we said they are different. But because we failed to reject it, we are saying they are the same. Because if we did not reject this, it means technically that we are accepting this to be correct. So they are the same because that's what the null hypothesis says. Since we did not get the null hypothesis, we're going to state our conclusion to agree with what the null hypothesis says. Okay, so that is that. And there's a part C still.